Hello everyone, I hope everybody is fine. Welcome to another lecture on the topic of techniques of limit computation. So in this lecture we want to discuss a new technique, a new method of finding limits of different functions. It's called change of variable method, also known as substitution method. We want to find the limit of 2x plus 2 all over 1 plus cube root of x when x approaches -1. So we did have functions in the past involving radicals, in particular square roots, and we learned about the rationalizing method. But here, instead of square root, we do have a cube root. And the first thing we are going to try the direct substitution method, but unfortunately the numerator approaches 0 when x approaches -1, and also the denominator approaches 0 as well, because cube root of -1 is just -1. So basically this is in the form of 0 over 0, which is the indeterminate form, of course. So in order to solve these kind of limits, find these kind of limits, we are going to change the variable. So I'm going to let cube root of x equal to some new variable, such as m, for example. So m is a new variable we are introducing. And I'm going to say, if that is the case, then if you raise both sides of this equation to the exponent of 3, you get x equals m cubed, clearly. And then we can say if x approaches -1, then we're going to find out what m approaches. Well, you know that x is m cubed. So if x approaches -1, m will approach cube root of -1, which is -1 itself. And this is just a coincidence that in this case, both x and m approach -1, the same number. And that is only because cube root of -1 happens to be -1. Oftentimes, m would approach some other number. So with this change of variable, we are going to rewrite the limit. So it's going to look like limit of 2. Instead of x, I'm going to substitute m cubed plus 2 all over 1 plus m when n approaches -1. Okay, so you see that we did end up with a new limit instead of the old limit. The old original limit did include cube root of x. This new one, thanks to the change of variable method, does not include any radical of any sort at all. So we're only dealing with polynomials. I know that this limit is in indeterminate form because when m approaches -1, still the numerator approaches 0 and the denominator approaches 0. So still we haven't solved any problem. Still, this limit is in indeterminate form, but let's admit it that there is no radicals there. So in the numerator, I'm going to factor 2 out. So I get m cubed plus 1. In the denominator, we just have m plus 1. And then in the numerator, we have sum of cubes clearly that we can perhaps factor. So it's going to be m plus 1 times m squared minus m plus 1 all over m plus 1 when n approaches -1. So if you simplify this rational expression, canceling m plus 1 from top and bottom, you end up with limit of 2 times m squared minus m plus 1 all over 1 only. So if m approaches -1, m squared would approach 1, and negative m would approach also 1. So we will end up with 6 as the final answer to this limit. Okay, so originally we did have cube root. We thought it's going to be very difficult, but thanks to this method of change of variable, when we substitute m for cube root of x, then that original limit is converted into a limit where we have polynomials in the numerator and denominator. And using the factoring technique, we can, of course, find the answer. You just have to know how to factor m cubed plus 1, which happens to be a sum of cubes. We should be familiar with sum of cubes, difference of cubes, identities, so that we can factor easily. There's another question here. I think we can use the same approach. So I would say, again, first of all, if you use direct substitution method, the numerator approaches 0, the denominator, which is cube root of 8, that is 2, minus 2, would also approach 0. So we know that this limit is 0 over 0. So we need to apply a certain method to find the limit. And that method is change a variable. So I'm going to let cube root of x equal to m again. And then I'm going to raise both sides to the exponent of 3. This means that x is actually m cubed. Same type of exercise, basically. And then I'm going to say if x approaches 8, then I will determine what m approaches. M would approach cube root of 8, which is 2. So this time you see that the numbers are not the same. In the past exercise, it was just a coincidence that both x and m approached -1. That is not the case all the time, as you clearly see in this exercise. So we end up with our limit as a limit of m cubed minus 8. I substitute m cubed instead of x minus 8 divided by m minus 2 when n approaches 2. We still know that this is indeterminate form. We're going to proceed with the factoring technique. The numerator is a difference of cubes, as I said earlier. So it will be factored as m minus 2 times m squared plus 2m plus 4 all over m minus 2 when m approaches 2. After canceling out m minus 2 from the top and the bottom, whatever is left over will be written, of course, and then we end up with 12 as the final answer to this limit question. Okay, there are a couple of other exercises there. This is another one, this is another one. So here again I attack the cube root. I'm going to say let cube root of x minus 4 equal to z maybe. And you know that if x approaches 12, 12 minus 4 is 8. Cube root of 8 would approach 2, 2 minus 2 is 0. The numerator approaches 0. The denominator clearly approaches 0. Therefore, this is, of course, indeterminate form. So that's why we need to use this change a variable method to find the limit. So if you cube both sides, you get x minus 4 equals z cubed. And then you're going to say if x approaches 12, then z approaches what? You're going to find out. If x approaches 12, then z would approach cube root of 8, which is 2. All right? So we're going to say this limit is equal to limit of z minus 2 all over 12 minus x. But what is x? Well, x, we can find it from here. X is actually 4 plus z cubed. So I can substitute 4 plus z cubed in the denominator. So instead of x, we substitute 4 plus z cubed. And here we say that z approaches 2 because the independent variable is not x anymore. We don't say x approaches 12 anymore because we changed the variable. So when you change the variable in the function in front of limit, you have to say that the new variable, that is z in this case, approaches what number. You can't say, the old variable x approaches 12 because there is no x anymore. We did change the variable. X is history now. We're dealing with a new variable called z. Okay, let's simplify this to see what we get. We get z minus 2 all over. So that's going to be 8 minus z cubed as z approaches 2. So what did we do? We let cube root of x minus 4 equal to z. we cubed both sides. We got x minus 4 equals z cubed. And from there, x was 4 plus z cubed. So in the denominator, instead of x, we plugged in 4 plus z cubed. So we end up with 8 minus z cubed in the denominator. Now, if z approaches 2, both top and bottom approach 0, obviously. So I know we haven't solved the problem yet. Still, it's indeterminate form. However, there is no ugly cube roots, in the equation. Okay, so to continue, we're going to say this is limit of z minus 2. In the bottom, we have 2 minus z using difference of cubes identity. We're going to factor it. It's going to be 4 plus 2z plus z squared, okay, when z approaches 2, okay? That's how you factor a difference of cubes. 8 minus z cubed equals 2 minus z times 2 squared, which is 4, plus 2z right there in the middle, and plus z squared. Now, z minus 2 and 2 minus z cannot be cancelled directly because one is negative of the other. One is opposite of the other. So if I factor negative 1 in the numerator, it becomes negative brackets z minus 2, right? Let me show the work. It doesn't harm. So I go negative and then 2 minus z. In the bottom, we have 2 minus z times whatever we had before. So now perhaps we can say 2 minus z from top and bottom cancel each other. So what is left in the numerator is simply negative 1. In the denominator, 4 plus z squared plus 2z. Order doesn't matter. So that is 2 here. Z approaches 2. So we get negative 1 over 12 as the final answer for this limit. Okay, just another question showing how we deal with cube root scenarios. This last one is challenging, okay? Why is it challenging? Because if you let cube root of x equal to some variable, then what are you going to do about the square root of x? Like, what are you going to substitute later on? When you have leisure time, try to do it by yourself so you see what I mean. And if you let square root of x equal to some new variable, what are you going to do with the cube root of x? So in this case, as I said, this is challenging. Usually we give these questions on the test. I'm revealing a secret, but it's okay. I'm going to tell you how these kind of questions are done. So here, first of all, we know that it's indeterminate form, okay? We are going to let t equal to the 6th root of x, okay? You can choose any expression to set equal to your new variable. In this case, I picked t. Nobody says it has to be always cube root of x, In this case, I use an innovative idea and I let t equals to the 6th root of x, and you'll see how I'm going to benefit from this. If you raise both sides to the power of 6, it's going to be x. That's very clear. Now, watch what happens here. Square root of x is actually x to the exponent of 1/2. So if you raise t to the power of 6 to the exponent of 1/2, it's going to be t cubed, believe it or not. And cube root of x is when you're raising x to the exponent of 1/3 on the right-hand side. And if you raise t to the power of 6 to the exponent of 1/3, that's going to be t squared, believe it or not. So you see that both square root of x and cube root of x can be expressed in terms of expressions of t. So I can say this is actually limit of, in the numerator, I'm going to write t cubed. In the denominator, beautifully, I'm going to write t squared minus 1. Now, needless to say that if x approaches 1, then 6th root of x would also approach 1. So t would approach 1 again. So I'm going to say t approaches 1. And this is the new limit I have to take care of in order to find the limit of the original function. Thank God, there is no square root, there is no cube root here. This is a fantastic method. So I'm going to continue. Still, it's indeterminate form, mind you, but I can factor the top and the bottom. So that's t minus 1 times t squared plus t plus 1. That is factoring using difference of cubes. And t minus 1 times t plus 1, that's factoring using difference of squares. We know all these identities from before. T minus 1 cancels out, obviously. So we get t squared plus t plus 1 all over t plus 1. T approaches 1. Okay, so the numerator is going to approach 3, right? And denominator will approach 2. And the answer to this question, final answer is 3 over 2. Okay, so we factor the numerator using difference of cubes. We factor the denominator using difference of squares. And then we cancel out t minus 1, which was the common factor in the numerator and denominator. Then what was left over was limit of t squared plus t plus 1, right? And in the denominator, we had t plus 1. And direct substitution method does work this time. And by direct substitution, we get the answer as 3 over 2, final answer. So this was not an easy question. There was a cube root and a square root both present at the same time in a function. But thanks to this change of variable method, or substitution method sometimes it's called, we could change the variable to t. We could define 6 root of x to be t, and from there we, of course, changed the limit to limit of a function that has polynomials in the numerator and the denominator instead, which is much easier to take care of course. And then by factoring, we could find the answer easily. So I did 4 exercises here. I say it's more than enough. I hope you also learned this technique. Usually this is not in the textbooks, but anyhow, I thought I share this technique with you. It's a neat one, and you can solve all sorts of challenging questions, I tell you, with this technique. I hope you learn this method and keep practicing, and thank you very much.